Okay. So before we can do section 5.1, the mean value theorem, we're on a new unit of semester. Units 1 through 5 are the derivatives, 6, 7, and 8 are the integral, which is the antiderivative. The first thing you guys have to be very confident is given a function like f of x, you have to be able to find the average rate of change and the instantaneous rate of change fast and be confident which is which. So if I ask you guys to find the average rate of change of this function, which is a quadratic, right? And if it's average rate of change, I have to tell you what are your x values on the interval. So we're going to be going from 1 to 5, that's your x1 and x2. How do we do this? AROC equals. What do we do? Okay, so it'll be f of 5 minus f of 1 over, okay, so it's something over 4 for sure, right? F of 5, we could plug in calculator mental math. If you plug in a 5 up here, 5 squared minus 4 times 5 plus 5. 10 minus, if you plug in a 1, 1 minus 4 plus 5, 2. So you get 10 minus 2 is 8 over 4. 8 over 4 is just 2. So your average rate of change is 2. There's no doubt about it, right? AROC, average rate of change. If you guys get that question on the AP test, which you will, you want to be decisive. Make sense? Okay, so speaking of that, you want to be equally decisive if you see the word or phrase instantaneous rate of change. What immediately should that spring to mind? The derivative of the thing you were looking at. So we had f of x, so the instantaneous rate of change would be f prime of x. The general equation of that, you'd use the power rule and you get, okay, great, right? Beautiful. Now, here's where we're going to go forward with this. What I did to save time is I graphed you f of x. This is x squared minus 4x plus 5, the parabola, correct? In blue, I connected x1, which was 1, and x2, which was 5. I'm going to make that a little bit darker right now. That was right here. And the average rate of change, the average rate of change between those 2 points we just found is what? 2. So you already have that. That's this dashed line. It's 2, right? Now, the question says, is there a value of x? Is there a position such that the instantaneous rate of change, which is the IROC, equals the average rate of change? Is there a place on the graph where the instantaneous rate of change equals the average rate of change? Question mark. Well, we just found the average rate of change from 1 to 5, didn't we? What is it? Just 2? 2. Okay, what's the formula, or the function rather, for the instantaneous rate of change? Okay. If we use this equation or setup, does that permit us to solve for x? Absolutely. Add 4 to the other side. So you get 2x equals 6. Divide by 2. X equals 3. Okay? So what does this have to do with anything? If you look on the graph and find where x is 3, when x is 3, we are right here. If we draw the tangent line, which is the instantaneous rate of change, that will have a slope of 2. They're parallel. So what we've just shown is, yes, indeed, there is a spot on f of x where the instantaneous rate of change, the tangent line, is equal to the average rate of change, which is the slope of the secant line. They both have a slope of 2. What's the big difference? The secant line connects 2 points, its average rate, versus the tangent line goes through 1 point is the instantaneous rate of change. So it's the difference between having an instantaneous speed like you were driving, right, at 30 miles per hour versus averaging 30 miles per hour. If you average 30 miles per hour, you went probably above and below. If not, you couldn't average it because you do have to stop for red lights and stop signs and such, right? Okay, well, this is a visual illustration. This is visually the mean value theorem. This is visually the mean value theorem. Okay? So the mean value theorem says this. Above, we were able to find a value where the average rate equaled the instantaneous rate. So now we're going to wonder, is that always the case? Does every function illustrate this? Yes. Well, there are preconditions, but yes, calculus assumes real numbers. There's preconditions. Okay, so the basis of the mean value theorem is the following. It's the average rate of change equals the instantaneous rate of change, like the picture. And this is called an existence theorem. Existence theorem. And this type of theorem is important in mathematics as they guarantee that a value exists. Okay, it guarantees. But there are prerequisites. There are prerequisites, which we'll get into. Okay, an existence theorem guarantees that a value exists. So there are two in Calc 1. This is one, mean value theorem, also abbreviated MVT. And we did study one earlier, which was called the IVT. So we will contrast and compare them today. That's our goal. Okay? Now, these are fun. This is going to, if you really think this is going to plant the seed, the directions here says the following. Take the 2 points that were given and to the best of your ability, connect them with a straight line. So something like that. The slope is what it is, okay? The slope would be the average rate of change, right? And we could figure it out. We could count the rise over run. I think it's 3 over 5. That's a 3/5, correct? Well, can we or can we not? Can you guys find a single point somewhere between those two, right? So if we called this A and we called this B, somewhere between those two, can you draw a tangent line that would have that exact same slope? Do you think it's possible? Okay. I heard someone say somewhere between, like somewhere here, the tangent line would look something like that. Does that have the same slope? Yep. So it's doable. It's doable right there. You guys believe it? Okay, what you're looking at is you're looking at a visual illustration of the mean value theorem, but I need to tell you more about it. Well, let's go back to, not go back, let's go to the next one. If you guys try to freehand connect these two, the slope is what it is, right? It is what it is. Okay, I had it good and then it got messed up. Okay. We can figure that out. That's up to over. That's a 2/9 slope. Can we draw a tangent line somewhere to the graph of g of x that has that same slope? Well, this is all made of straight lines, right? Segments. So this here has a negative slope. That's wrong. This one here is too steep. This is, you can't. If you think you're slick and you'd be like, well, Hanson, what about here? You can't draw a tangent line to a cusp. It's not differentiable there. That's too sharp. The cusp is undifferentiable. So in this picture, you actually cannot execute my objective. You cannot draw a tangent line with that same slope. You can't. So what actually you're going to come to learn is the mean value theorem is not applicable to this drawing. What disqualified it? Not differentiable at the cusps, okay? Yep, circle M cusps. Okay, we got a couple more pictures. Okay, if we freehand here. Okay, close enough. Yeah, that's pretty cool, huh? Okay, that slope is what it is. That represents the average rate of change. Can you guys draw a tangent line through one and only one point that would have that same matching slope? Probably somewhere around x equals 4 to 5-ish. Somewhere. It's hard to say exactly. Somewhere in there, right? Okay, again, what's the goal is it's only supposed to go through one point. It's really hard to do it by hand. Something like that. Do you know what I'm trying to get at? So again, we were able to do this. You're showcasing the mean value theorem. Any ideas why we were able to do it on this one and not the other one? Yeah, it's differentiable everywhere on the interval, correct? It's nice and beautiful and smooth and differentiable. Okay, one more compare and contrast. Look at this last one. If you connect this point to this point, it's pretty steep. Man, doggone it. What would that slope be? Is it 8 over 2? 8 over 2 is 4, okay? Is there some place between those 2 points, that's close enough, that you'd have that same, draw a tangent line with that same slope? I don't think you can you? You know, it's too bad this thing stopped because if it kept going, we probably could right about here. Do you know what I mean? But that's coulda, shoulda, woulda. You can't. So the mean value theorem is going to be disqualified. What kind of disqualified it do you guys think at this point? That doggone jump, which means it's not differentiable and it's not continuous. But it is differentiable. It is differentiable all in here. It is, but it's not continuous at the endpoint. That was a disqualification. So the MVT is not going to work for this. Okay, so if you're kind of picking up what we're putting down, what seems to be the prerequisites to invoke this mean value theorem, which you're trying to show the instantaneous rate of change equals the average rate of change. So I would say, like, what are the prerequisites? Prereqs. I don't know how to spell it. The function has to be continuous on the interval and, well, you guys are amazing. It has to be continuous and differentiable. And differentiable, both. Now, unfortunately, a little bit of getting into the weeds on the interval notation on this, it is a little bit painful, but I made a picture during lunch, which I think we can talk about. We'll see. Okay, so that was excellent brainstorming. Very good. So what is the mean value theorem? If, these are ifs, these are the prerequisites. If the function is continuous on a closed interval, we'll look at that. We'll look at what that means. And differentiable on the open interval, which means that you don't have to consider the endpoints. There does exist some number in the open interval such that the f prime, which is the instantaneous rate of change derivative, equals the AROC, the average rate of change. Okay, this is the mean value theorem, aka MVT. Okay, the little bugaboo I have about this is the fact that the prerequisite is continuous and differentiable, that's no problem. but the interval is closed and opened respectively. That's a little bit of an annoyance. The MVT guarantees that the instantaneous rate equals the average rate somewhere in the interval. It's called an existence theorem. It guarantees something will occur, but does not specify where. Okay, and we'll approach this in a way we approach the IVT. We'll check conditions, check endpoints, state the conclusion, etc. You kind of have to be very meticulous about this if it were an FRQ. So in plain English, think about this. In plain English, if you drove to Pioneer averaging 30 miles per hour, did the speedometer ever register an instantaneous rate of exactly 30 miles per hour? 100%. It had to. Because how can you average 30 miles per hour unless you went below and above, which means you went through it, because speed cannot jump, it's continuous. It's just like if I look right now, if the temperature is 27 degrees Fahrenheit right now and it goes up to 36, right? There's some average in between there, and you would have to have crossed that temperature in order to average it. It's just the way that it is. Okay? So here's what we're going to do now, and I'm going to purposely cut this off. I confused myself so bad second hour. This table here is for questions A and B, and the next table is for the next problem. I formatted it real bad, but it is what it is. So this is what we're looking at. I'm giving you a table of what? F of x. Okay, that's its name, F of x. For the following problems, read the info and determine which theorem, IVT or MVT, would apply. All right, question A. The function f is continuous. So they let us know that it's continuous, and they're only giving us selected values of x, but the function is continuous. But did it say differentiable? It did not tell us that. Selected values are given in the table. Is there some time between 1 and 7 such that f of c is equal to -2? Can we be confident beyond a shadow of a doubt? Convince me. You can't go from 5 down to -4 without passing through. Correct. In fact, I hate to do this, but to give you guys a little secret, College Board usually writes these where you really typically, not always, can just look at the beginning and the end. At time 1, we're at a position of 8, and at time 7, we're at a position of -4. So if we start at 8 and go down to a depth of -4, do we pass through -2? You have to, if it's continuous, which it is. What theorem is this invoking? This is the IVT. Yes, this is Intermediate Value Theorem. IVT. So how do we write this up? This is what's kind of tedious. Okay, this is what I'm not always good at. We can put the Intermediate Value Theorem can be applied. We're going to write this. Intermediate Value Theorem, IVT, can be applied since what? Good. That's the precondition. Since f of x is continuous, I'm just going to write CONT. Is that okay? Okay, that says CONT. That's the prerequisite. If we don't know that, we cannot draw it. Okay? So we stipulated f is continuous, correct? So now we can say we are guaranteed some f of c equals -2 because why? Yeah, because f of c equals 2 is between, f of c equals -2 is between what? F of 1 equals 8 And, okay, I think that's very thorough. Is that good? Full points. That's a beaut. Hey, I'm sorry I formatted this so bad. We barely have any room to answer B, but we won't need much room. Okay, question B says, is there a time on the interval 1 to 7 such that the derivative of f is -2? Well, to take the derivative, we'd have to be guaranteed differentiability. So this is kind of alluding to the mean value theorem. But to invoke the mean value theorem, you have to be told the function is differentiable. Did they tell us that anywhere? Scrutinize it. No, no. So there's no guarantee. We have no guarantee. It might be. I would say there's no guarantee. Or you don't know. You can't say no, you can't say yes. There's no guarantee because we don't know if it's differentiable. So I'm going to put it differentiable question mark. Differentiable question mark. They didn't tell us it was not differentiable. Do you know what I mean? They just didn't tell us that it is. So we're like in limbo. Not enough information, inconclusive. Moving on. Okay. All right. Now we're using this. Now we're using this table. This is a brand new problem. Okay. In this problem, what do they tell us? What are we looking at? It's a table of time versus velocity. It's velocity versus time on the x and velocity on the y. Okay, got that? For times greater than or equal to 0, the velocity of a particle moving along a straight line can be modeled by the differentiable function. Okay, now we're talking. Now here's a throwback. If they tell you a function's differentiable, is it automatically continuous? Yes. So this implies continuity. Must there be some time on the interval from 2 to 11 such that the acceleration is -1? Acceleration is the derivative of velocity. So v prime of k equals a of k, which equals -1. And we have continuity, right? And differentiability. Continuity and differentiability, right? So does that mean, can we invoke the mean value theorem? So mean value theorem, bless you. What does that mean, basically, in a nutshell? If the function is continuous and differentiable, which we were told it is, at some point on the interval, the average rate of change must equal the instantaneous rate of change. Okay, now we're talking. Well, they gave us the instantaneous rate of change. That's the derivative, correct? Which is -1. Can we show that the average rate of change is also -1? Now, College Board doesn't get too slick with it. You can typically just use the beginning and the end. So what if we do change in velocity would be 4 minus 13, and change in time would be 11 minus 2. 4 minus 13 is -9, and 11 minus 2 is 9. What's -9 over 9? Check. So it works. Do you see what I mean? Okay. So there must be a time due to the mean value theorem. So the hard part about this, quite frankly, is how can you write this up? The MVT can be applied, correct? So I'm going to write MVT can be applied since V of t is differentiable for all values of t, for all t. So at some point, the acceleration, which is also the derivative of velocity, is equal to -1. And so is the average rate of change, which was v of 11 minus v of 2 over 11 minus 2. Okay. This here is the instantaneous rate of change, and this here is the average rate of change. Is this true? Yeah. So we're still not quite writing these up quite exactly perfectly correct yet, but we're getting there. Okay? All right, let's keep going. Now, this is an aside. I did not do this with the other classes because I didn't have this ready. I made a little picture here. I want to chop this up with you guys. Tell me if this makes sense or not. Because the open and closed intervals are really painful. Okay, I believe this chart is correct. I just made this up. So this is just something to like noodle around your head. I claim this little sketch I made is not continuous on the closed interval from A to B. The closed interval means A and B are included, right? So if you put your pencil on the closed point A, does that connect to the closed point B? No. They do. The closed points don't connect, so it's not continuous on the closed interval, but it is continuous on the open. The open means the endpoints are not included. So if you don't include the actual defined point A, it's beautifully linear between A and B, is it not? Do you see the difference? Think about it. Is this function differentiable on the closed interval A to B? Remember, closed means it's included. Can you take the derivative at point A? Because of the jump, it's disqualified, right? But is it differentiable on the open interval A to B? Yeah, because the slope would all be the same. So it's the same. So kind of think about that. Does the difference between considering the endpoints or just looking in between, does it make a difference? It does. It does. So here's, what does this have to do with the mean value theorem? Let me try to draw you a picture. Okay, you guys don't have this in your notes because I just came up with this at lunch. If I switch to pink, right? And if I draw a line between here and here, and that's not going to work because it was too bad of a job freehand. Let me try again. If I draw the secant line, this would be the average rate of change from where to where? A to B. What kind of rate of change is that? Some average rate of change. And what kind of value would you ascribe to it? Some negative, correct? Well, that's a negative, correct? But what are all the rates of change instantaneous between A and B? Positive. So this, you could not use the mean value theorem. It doesn't work. Why doesn't it work though? Correct. But what screws up the picture? The jump at A. So to not have this happen, because what does the mean value theorem do? It is a guarantee, right? So for the handshake guarantee to work, it has to be continuous on the closed interval so you don't run into this dilemma. Okay? This is the most kind of in the weeds confusing part of it, but it's not really worth losing sleep over, but this is what it is, it is what it is. Okay, so compare and contrast IVT versus MVT. What are the differences? What are the similarities? To invoke the intermediate value theorem, the only precondition you need is continuity or the nature of being continuous, continuity. Okay. Now contrast that with the mean value theorem. What is that predicated on? Yeah, you have to have both continuity and differentiability. I don't know if I can spell that. Differentiability. Woo! Okay, what are some of the tells on an intermediate value problem? It's mostly going to be like conclusions about values in a table that are not shown. That's a tell of when to use this. Conclusions about values in a table not shown, right? Versus in the mean value theorem, what's a tell on that? Conclusions about, yeah, IROC and AROC, so rates of change, right? Conclusions about rates of change of the function in the table, of the func in the table. Okay? So let's do one at a time. Let's do an intermediate value theorem. Okay, and think about the notes we just took, the tells. Okay, a bug is moving along the x-axis. The bug's velocity is differentiable, which also implies continuous, and selected values are given in the table. Is there a time on the open interval 0 to 9 such that the velocity is exactly -1? Why? What's your argument, Ben? So the velocity starts at 5 and ends at, so if it starts at 5 and ends at -4, did it have to go through -1? Yes, because it has to go through all velocities in between 5 and -4. Which theorem is this invoking? IVT. Okay, what are the preconditions? What did they tell us? They told us that it is differentiable. So they said V is differentiable on what interval? On the open interval 0 through 9, which means that V is continuous on the closed interval 0 to 9. You can't take the derivative unless you have continuity on both sides. So if it's differentiable on the open interval, it's continuous on the closed. I know some of this is kind of getting into the weeds. It's not enough to ruin your day. Okay, and so we know V of C equals -1 is between what? Okay, this is getting, the battery's getting low, is between V of 0 equals 5 and V of 9 equals -4. Is this all true? Yes? Okay, so then that's your work. What's your final statement? Since V of t is what makes or breaks the intermediate value. Since V of t is continuous, on the closed interval 0 to 9, the intermediate value theorem, IVT, guarantees that there is a time. Oh, this is so frustrating. There is a time time c for 0 is less than c is less than 9, such that v of c equals -1. Okay, that's a very long-winded way of saying that you can't pass through -1. You can't go from 5 to -4 without passing through -1. The temperature can't go from 5 degrees to -4 without crossing through -1. Temperature is continuous. It doesn't jump. Okay, let's compare that to the one on the other side. The one on the other side. What was going on in that one? What was the table measuring? Velocity. What was the question? Acceleration. What's the connection? Yeah. What's the derivative of velocity? Yeah. So this is the table. You're looking at a rate, velocity to acceleration. So what do you think this one's hinting at? MVT. So the work would be V is differentiable. I'm just going to put DIFF on the open interval from 0 to 9, which implies that it's continuous on the closed interval. It's continuous on the closed interval, 0 to 9. Okay. So let's look at the, so basically what does the MVT say? Based on these preconditions, at some point on that interval, the average rate of change has to be, what instantaneous rate of change do they want it? And the average rate of change would be change in y over change in at the beginning and end. So let's see if the time would be 9 minus 0, and you do get -9 over 9, which is, okay. So now how do we write this up so it's real slick, slick, slick? Differentiable on the open interval 0 to 9, which implies that it's on the closed interval 0 to 9. I know this is frustrating. The value theorem, the MVT, guarantees that there is a time which we call letter C on the interval 0 is less than C is less than 9, such that, not Sue, such that, what? The average rate of change, which we could say is V of 9 minus V of over 9 minus 0 equals the instantaneous rate of change, which is V prime of C, which in turn is 1. Okay, I know these are tedious, but I didn't do this in past years. I know this is how I had so many students get a 4 last year, half of my roster. How many of those could have gotten a 5? Just one question like this, one little thing. It's the difference, you know? Okay? All right, we're gonna move fast. Fast. 3 more questions, fast. Okay? Real fast. Ready? Here's your tells now. I go fast. I'm gonna kind of be a bad student, and I'm not gonna read it first. I'm gonna notice what's the table measuring. G of X, what's the question measuring? G prime, they're not a match. To be IVT, they have to match. So probably MVT. I'm gonna put MVT question mark. Okay, so MVT, if that was the case, you're looking for average rate equals instantaneous rate, which looks like it's the case because the instantaneous rate they gave us is 2. So I'd have to prove the average rate is 2. Do you think we can do that? Okay, so this would be 10 minus -2 over 6 minus 0. 12 over 6 is check, right? So we can say since G is differentiable on 0 to 6 and continuous on brackets 0 to 6, right? MVT guarantees a time C such that what? G prime of C equals the average rate of change, which is G of 6 minus G of 0 over, and both of those must equal 2. So it's kind of like that picture I showed you. If it's not continuous at the endpoints, you can have that jump which breaks the guarantee. Okay, we'll look at the picture again tomorrow. No, this is an open. 0 to 6 parentheses is open. 0 to 6 brackets is closed. Did I misspeak?
No.
It's confusing. It is confusing. We can look at my picture. We can look at my picture again tomorrow and argue about it. Okay, example 4, fast track. What's the table measuring? F prime. What's the question asking? That's a match. It's probably IVT, correct? What's the precondition for IVT? Do we know that? Yeah, so since it's differentiable, since F prime is differentiable on 2 to 15, right? Then it implies that it's continuous on 2 inclusive through 15 bracketed closed interval, right? Yes. Okay. So what can we say then? The IVT guarantees a time. They changed the letter here to K. See, they changed it to. It's not a big deal. If you wrote C, they'd mark you correct. They guarantees a time K, um, such that, yeah, such that f prime of K is equal to 5, right? Since, yeah, you know what? That's a tough one, probably, but we already did establish the intervals here. So is that implied? You know, IVT guarantees a time K, probably on the interval. You're really right on the intervals, right? Such that f prime of K equals 5 since f prime of K equals 5, the redundancy does frustrate me, is between what? f prime of f prime of 2 equals 1 and f prime of 15 equals 6, which implies that 2 does, or 5 rather, falls between 1 and 6, right? Got it? Okay, very last one for contrast's sake. Okay, fast tracking it. What is the table measured in? L prime. What does the question ask for? L double prime. L double prime is the derivative of? No? Okay, let's hold on. The table is L prime, question asked. So it's the derivative of L prime. So this is a rate of the table, which would be probably MVT. So we have to establish, we could say that L prime of, well, did they tell us right here? What? The differentiability is continuity is brackets. Yes. L prime of t is differentiable on open interval 0 to 8, so it's continuous on bracketed closed interval 0 to 8, period. Okay. So the MVT guarantees a time C on 0 to 8. See, the redundancy, I shouldn't say this, but it does irritate me, but Eli is right. You're supposed to reiterate the interval. MVT guarantees a time C on the interval 0 to 8 such that what? L double prime of C equals 0, right? Okay, you could put because L prime of L prime of rate of change equals the instantaneous rate of both equal 0. However, I cheated because we never showed that. Did we ever show that? We'd have 6 minus AROC. If we show this, we get no credit. 6 minus 6 over 8 minus 0 equals 0 over 8 equals 0, which does equal the IROC. If that was actually, I'm kind of glad I did that to showcase that. That's like the pinnacle of the work. If you don't show that, the whole thing's for naught. That's all hogwash. Okay. Where does it say?